additive manufacturing. My name is Matt LeMay. I am part of the Autodesk Generative Adoption team, and I'm here with the team from Penumbra Engineering who worked on the project and the use case we'll be talking about today. So to start off, we'd like just a quick round of introductions from all of the presenters today. So I'll hand it over to the team from Penumbra.
Hey, how's it going? My name's Steven Smetzik. I am co-owner and design engineer from Penumbra Engineering. There's a little bit of my background right there. Bachelor's of Mechanical Engineering from Northern Arizona University. Background in aerospace and product development. And currently also involved with the Arizona Technology Council, the Additive Manufacturing Committee. And I'll pass it over to Dean.
Hello, everyone. My name is Dean Pierce. I'm the other co-owner of Penumbra Engineering, and I'm the development engineer. I too have a bachelor's in mechanical engineering and a minor in biological sciences from Northern Arizona. And I've been working in the aerospace industry for a number of years, have a test and analysis background there, and love very much being able to work on challenging projects and, challenge ourselves. And pretty much been moving through this thing with Steven for a number of years now. And we're loving this new collaborative effort that we're trying to push. And we're very, very excited to present for you today.
Thank you, guys. And this is Matt LeMay. So again, I'm on the generative adoption team here at Autodesk. So I work with a lot of our customers to help them understand how to use generative technology effectively. My experience since working at Autodesk over the last 3 years, prior to that, I was a mechanical engineer working in the aerospace composites industry, as well as additive manufacturing. So just a quick agenda for the presentation today. We'll start off with an introduction to generative technology. We'll talk about why Autodesk is moving down that path and what the advantages are. We'll then take this case or this use case we'll be presenting today, and we'll cover the entire workflow from thinking about the problem itself to setting up the generative solve to exploring options and then actually having to produce those as well. And then we'll leave about 10 to 15 minutes at the end of the presentation today for Q&A. So just want to let everyone know that you are currently on mute. If you do have a question, please feel free to type it into the Q&A window or to use the chat window within the webinar link. And we will make sure to address those questions at the end. So to move forward, I just wanted to launch our first poll question of the day, and this should be coming up on your screen now. The question is, what is your current level of experience with Autodesk's generative technology? So it could range from none to advanced. We'll wait a few more seconds as people are still answering. And closing the poll now. So took part in that poll. It looks like the vast majority of people are pretty new to generative technology within Fusion, which is a great thing, and that's why we run the webinars like the one that we're doing today. So first, again, we'd like to cover a quick introduction to generative technology. So as many of you might be aware of, Autodesk has been making CAD solutions for a little over 35 years at this point. And CAD has always been a way for an engineer to take the ideas that they have and really to put them down on paper. So we've always been constrained on the production processes that we're actually producing our parts with, and we're constrained with the ideas that we can have as humans, really. So as we look towards the future and we look at the growth of additive manufacturing, Autodesk realized that we need a new set of solutions that allow us to actually explore all of these brand new opportunities that we have. So the idea with generative technology is that it's actually a co-creator within the process. So rather than you creating the part itself, you're creating the loading conditions, you're creating the geometries you need, and you're allowing the generative technology to then explore ranges of options and manufacturing types that you probably wouldn't have thought of yourself. So the traditional product cycle that we're really trying to adjust, you're seeing on here, many of our customers would take a small handful of concepts, it could be 3 or 4, and they start evaluating those for manufacturability, for the integrity of that part. And in the end, they're bringing a product to market that may have taken them longer since they didn't have a lot of concepts. And it might be compromised for some of those manufacturing processes. Maybe they weren't exploring all of the options. So, what we'd really like to produce on the generative technology side is rather than a small handful of concepts, generate hundreds or thousands of options very early on within a product cycle. So teams of engineers can explore options that they would have never thought of in the past, creating outcomes like you see on the right that typically in the past we would have never thought of. So when you look at actually applying generative technology, there's a couple main advantages, and we talked about this a little bit over the last 2 slides. It's really about exploring a wider range of options. So we've always been constrained, typically through the manufacturing process, on what our products need to be. Now we can explore anything from additive manufacturing to 3 and 5 axis subtractive and a range of materials, so we can then start making trade-offs as opposed to continuously making the same type of product. Second to that would be planning for the additive manufacturing process. So we talked again about how the means of production are really changing. So generative allows us to truly get the most out of the additive manufacturing process and again, create a product that we wouldn't have thought of. And third to that would be a parts consolidation example. So generative also allows us to take what was typically multiple components within an assembly and generate an option to consolidate those into one single component. So just to show a couple use cases, many people might be familiar with the General Motors generative example, and this kind of highlights everything that we were just talking about on that last slide. So General Motors took that very conventionally produced seat bracket assembly to the top left, and they started generating options of what other kind of ideas could they explore. So in the end, they ended up generating a product that was 40 than the original, 20% stronger. It also consolidated that assembly from 8 components to 1, so saving them on their supply chain. But probably more important than all of those things, they were able to generate 150 viable options that they could then start making trade-offs for. So trade-offs for the manufacturing process and trade-offs for the kind of materials that they could produce this with as well. So to show the workflow for generative technology, this is a company called Wheel. And what they took is this seat bracket assembly and a very similar process. They first looked at what they needed to connect to and then what they needed to avoid. They set up their loading conditions. So again, this is walking through the entire process from left to right that you can see on the screen. They set their manufacturing processes. So exploring additive manufacturing, subtractive manufacturing. And then they could start solving and exploring options that, again, would be very unique to what they produced in the past. So that last image was a previewer prior to solving. And then after they've ran through and solved everything, they can get hundreds of options pretty quickly. And they can start making trade-offs for, again, the material type and then the manufacturing process as well. So one of the most important things with this process is that after you've generated a component and we are outputting solid usable CAD geometry that you can bring right back into your assembly. You can post-process like you're seeing on the screen. You can run a secondary FEA analysis if you need to, or connect it with additive and subtractive. So really the magic of this entire process is that we're not just creating a mesh that you would have to model over. It's truly creating usable solid CAD geometry. So here at the end of the video, you can see some of the CAM toolpaths created and then that final component placed on that assembly. So there's three main ways to find advantages using the generative technology process. Again, that idea, the first one would be exploring a range of options. So making trade-offs for materials, performance, and manufacturing types. Second would be through the parts consolidation ideas, similar to what we saw with GM. So taking 8 parts and consolidating that down to 1. And then the third is part enhancement. And this is where we'll actually focus today. So the reason that we chose the use case that we'll be presenting later on is that we think it's pretty unique and it's something that not a lot of people have explored yet. So this is an example where we have an existing component and we're going to use generative technology to improve strength and then reduce the mass of that component as well. So just to conclude a little bit about the introduction to generative technology. So what is unique about it? Again, the idea that we're exploring a range of options. So within one solve, we could get tens, hundreds, or thousands of options. We're exploring a range of materials and manufacturing types. And then what we get on the back end is CAD-ready tree that we can continue to work with. So as we move forward, I just wanted to launch our second poll question of the day. This is really just to find out who we have in the audience. So the question is, which one of these personas matches your role the closest? So maybe you're an engineer, you're in manufacturing, maybe you do everything, which is great. So we'll wait a few more seconds for everyone to answer the poll question. Okay, thank you for everyone that answered the poll. Be closing that now. So it looks like there's a pretty strong mix across the board. There's majority of people are on the engineering side, which is great, but there's also some within every one of those other categories. So I think what's really interesting on generative technology is that since it's combining upfront simulation with product creation and manufacturability, any one of the personas that we had on that poll question could find value within this process. So thanks again for everyone that answered that. So after we covered a quick introduction to generative technology, I also wanted to just provide a little information on how to get it yourself. The first thing, we do have a generative trial available, and I'll share this link at the end of the presentation. If you don't have a commercial subscription to Fusion, this is a 30-day commercial trial that has cloud credits to run about 1, maybe 2 projects. When you reach the point where you'd like to start learning how to use generative, we also have what's called the Fusion Adoption Portal. And the adoption portal is completely free, and it has tutorials that help you learn how to use not just the generative technology that we'll be working on today. It also has tutorials for Fusion in general, from anything from modeling to CAM. And I'll share that link at the end as well. And then finally, please feel free to reach out to me with any questions if you have questions on how to access the technology or how you can get started. And my email address is there on the screen. So with that, I'd like to kick it over to the team from Penumbra, and we can start covering the use case we'll be talking about today.
Oh, thanks so much, Matt. This is Dean Pierce again with Penumbra Engineering. I'm going to give you a little background as to who we are and kind of where we've come from. As both of us mentioned in the beginning, we come from the aerospace industry mostly, but in there we've got backgrounds in both design and test for all of this. One of the things that we're very proud of is being part of the Arizona Tech Council here and the Additive Manufacturing Committee here in Arizona. My co-owner Steven is a co-chair for that, and we've been trying to become as active as possible with regard to generative design amongst the community. and it's being received, and people are starting to dig deeper into it. And was talking about some of the larger corporations as well, which is very good. Everything is moving forward with that. We have a licensed professional engineer, that's me, and we've spoken at a number of different events, like the Additive Manufacturing Tech Council meetings down in Southern Arizona, the Business Expo, 10 West. All those things have been predominantly here in Southern Arizona, specifically in Tucson. And
and I was going to mention too that we actually did basically this topic at Autodesk University back in November. So we're excited to kind of keep going along this thread and taking that momentum from Autodesk University moving forward.
Yeah, I really hope that some of you out there are actually repeat offenders, and you may have seen Stephen and Matt speak over there at the event at Autodesk University a little while ago, and hopefully, you might recognize some of this content, but we're excited to present the new stuff to you as well. We at Penumbra, had many things that we've worked on over the years, and it's basically allowed us to hone our processes and have everything based around generative design and additive manufacturing in collaboration with a heavy and healthy amount of project management. That way, we can basically create a closed loop with regard to efficiency for how we design everything here. We believe very much in being able to take our clients and all the projects that we've worked therein to a whole nother level of efficiency through our project management and provide a very high quality and optimized design through generative design and additive manufacturing. And there's lots of different technologies that we've used in the past for that. We're liking a lot of the HP nylon MJF. That stuff's pretty great. And what we like to do is empower the use of additive manufacturing to help hardware companies develop innovative and performance-driven products.
All right, so now this is Steven Smetzik talking now. And so I'm going to kind of go into the use case that we've been promoting. So as Matt mentioned, this is kind of more along the lines of we're starting from a concept and not necessarily doing like an improvement on a part. We're going from the beginning of the conceptual stage of the part. So our client basically, so Perceptive Sensors Technologies, PST, they had a challenge. So their acoustic sensor technology is able to basically take an acoustic fingerprint of anything in a concealed container and basically tell you what it is to their database. But they wanted to take this older technology that was developed for the military and bring it into more of a consumer-facing industrial market. So this gave us the opportunity to kind of pair up generative design type advantages with that. Because this is more of a higher end product, we're able to mess around with the low volume manufacturing type strategy and really bring out all those benefits that come with generative design plus additive manufacturing. And so one of the big things that generative design allows you to do along with additive manufacturing is really tackle that improved strength. And so one of the baselines that we were able to do is start out with a traditional type plastic design where we had traditional ribbing, and then we were able to go over to generative design and create a bunch of new options. And then we were able to arrive at a result that was 78% increase in strength while also maintaining mass balancing. And so this product, it's a handheld, so a big portion of it is being able to have it so that it doesn't fatigue someone's wrist. So we're actually working with mass balancing. So the good part about generative design is that you can actually put mass targets, or you can basically go for the lowest weight, strength to weight ratio possible. So we kind of did a compromise there with the mass balancing to make a really, really good product that the technician out in the field could hold and not be fatigued. And then lastly, the design for additive manufacturing portion. So generative design, it can be applied to a lot of different areas, but with additive manufacturing, we have that design freedom to really create this unique product from the ground up. And we're using parameters through, and Matt will talk about this a little bit, the other product that Autodesk has, NetFab. We're able to go in and optimize it for build-ups to get the most, the best cost per unit. And go to the next slide. And yeah, so really what, kind of taking a few steps back. So that's kind of the use case, and we were able to deliver that product for them. But really the inspiration where we first heard about generative design and kind of this thinking and really being able to apply this to projects from the ground up kind of started back in 2013. This is a book that I like to reference people to. It's called Fabricated. And really this book really showed that the multi-jet fusion technology, which we'll talk about a little bit more as we go through, is a powder-based technology, but it's really based off of voxels. And so that concept where you can actually apply different material properties along a composition of a part. And so HP, MJF, and HP in general, their kind of path is following this line of where we're going to be able to use generative design, create shapes that are optimized, complex shapes, but in the future, we'll also be able to take that a step further. And then, as you see there too, in 2016, generative design was taken out of Project Dreamcatcher, and you may have heard that if you follow Autodesk. And basically, that's generative design is the formation of that into an actual product that Autodesk is now using. And so the combination of this voxel type additive manufacturing technology plus generative design really combined together gives you this huge advantage when creating these new innovative products. And yeah, this is kind of doing an overview of why use generative and additive together. So for our client, really the hardest part is coming to them not only with good engineering data and for them to understand what the benefits are on that side, but also we want to understand it on the business side too. And so this is really how's the product used. This product is used in the oil and gas industry primarily, so it's really out in a harsh environment. This product needs to be able to be dropped, stepped on. So basically, we at Penumbra we generate our load cases with an understanding of how this harsh environment works, and then we apply that into the design to make it optimized. And then so the next advantage is this optimized design is easy to use too. Like I mentioned, the mass balancing. So it's balance designed to reduce the fatigue on the user. And the good part is too, is that this product was not intended to be produced in high volume. It was a low volume product. So you're talking, 1,000 units or less per year. And with multi-jet fusion technology, the cost per part makes this a viable option. And then also the additive manufacturing benefits continue on with being able to customize. So that lower portion there. So we have the upper body, and then we have the lower adapter. And the adapter actually needs to be able to be changed depending on how this product is coupled up against the container that you're taking the reading on. So that's another huge benefit. And then really the feedback and continuous improvement, as long as we have good data management, is that we can actually release this in versions and actually improve it with more data over time. And the low volume model actually allows us to do that even better. And then another big benefit too is we try to make this really simple to maintenance. So combining a lot of parts together where we could, try not to use a lot of hardware, so that if we needed to maintenance this, take it apart, replace some of the electronics inside, we could. So I'll pass it back to Matt now.
Great. Thank you guys for the introduction to the project. And just a quick note to everyone who's watching the presentation. Please feel free to use the Q&A window or the chat window to type in your questions while while we're presenting, and we'll make sure to address those at the end. So the team from Penumbra was just talking about the challenges that they were trying to address and how generative and additive could provide them with a brand new set of solutions. So now we'll look a little bit further into how we actually use the generative technology workflow to receive those results that they were looking for. So anytime you're using generative technology on a project and using this workflow from left to right, the first thing is we always need to set up our geometry space. So we need to think about what the generated geometry needs to avoid. So that could be other parts within your assembly, and then what it needs to connect to, which we call preserved geometries. Second would be the generate phase, where we are setting up our loading conditions. So Stephen talked about the harsh environments and some of the impact strengths that this part would need to hold. So we need to set up our loading conditions, know where it's constrained, know how that part's loaded, come up with a factor of safety that we'd like to reach. The third piece would be after we've generated all those options and we have a range of materials, a range of production processes, we need to explore and find the correct solution to move forward with. So there we can make trade-offs for performance, for manufacturing types, and for the material that we're using. Next, we need to post-process. So we talked about this a little bit at the beginning, is that the outcome that you get from generative design is usable CAD. So we need to take that usable CAD geometry right back into something like Fusion, and there we can post-process or make any final adjustments. And then finally, we need to fabricate. So in this case, we connected it with our additive manufacturing platform to then produce the components that you'll see moving forward. So to get started on this workflow, looking a little bit closer. So again, we talked about the first step that you always need to do on these projects is to take all of your geometry into account. You need to think about your functional and your manufacturing requirements. And you actually need to edit or create geometry to call out those obstacle geometries that we talked about. So to do that, we took the existing component, and what we needed to do was start to extract some of that geometry where we wanted generative to come into play. So here we took that conventionally produced part that had those pinned sections that you can see from that lower face, and we've essentially cut those away because we want a brand new way for generative to create all of those connecting features. We then needed to create material on the outside of this component, which we would call out as an obstacle geometry later, saying that we want the exterior of our component to look exactly the same as it currently would with a traditional process. And then moving forward, sorry about that, lost the slide. We need to then set up the generative solve itself. So again, we need to go through, call out what our preserves are. Our preserves, again, are the geometry that we know that we need to keep in. We need to call out our obstacle geometries, which again is the geometry locations that we need to avoid. We need to set our performance objectives, whether it's minimizing mass or setting a specific mass target, like we talked about for this project. We need to select our manufacturing types. So we've been talking a lot about additive manufacturing within this presentation. However, it's also very important to know that we can also set up subtractive manufacturing constraints as well. So we could put in 3 and 5 axis requirements. And then we need to set our material, the materials that we'd like to solve with as well. So just to show this quick flow that we were just talking about, all of that geometry that we've created, we're now calling out as the obstacle geometry, and that turned to red, meaning after the generative process is completed, there's not going to be any geometry that goes in those sections. We're then calling out what our preserved geometries are, and you can see that in green. So that's all of the geometry that we know that we need at the end of this solve. And then we start applying our loads and constraints. So we know when the adapter is attached to the handle, it's constrained on those faces that you see in the lock in the back, and then there's a pressure force applied to those front faces. So we would continue applying load cases, and then in the end, we had about, I think, 7 or 8 separate load cases that could correctly identify all of the structural needs that this part would have. So I'll fast forward this just a little bit. So we've applied, now you can see to the tree on the left, all 6 of our load cases. And moving forward, if you see the user interface at the top, everything is moving left to right. So after we've applied those load cases, the next thing that we would do is set our objectives for the solve. So here we talked about the ability to set a mass target, which is really interesting in this case. So we can say, generate me components that have a specific mass. In this case, we did 0.14 pounds. So that's allowing us the ability to then even out the mass on the top of the adapter and on the bottom, making it a really easy to use part for the technician. Next would be setting our manufacturing constraints. So here we know with the HP multi-jet fusion process, there's a minimum thickness requirement that needs to be met. And then you can see underneath, there's also milling constraints that we might apply just to see what kind of results we can get through that. So again, within one solve, we can set all of these manufacturing criteria, and we can also set a range of materials to explore as well. So in the end, we ended up going with HP nylon 12, but we can explore a lot more than that as well. We can say, show me the results if it was in if it was in a carbon fiber reinforced plastic, nylon 6, HP nylon 12. We can put in all of these different material options so we can explore what the performance improvements for each one might be at the end. So again, in the same way that we selected a range of manufacturing types, we can also select a range of materials to then explore. And when we're finished with that, so we selected up to 10, at that point, we would be ready to start solving. So the next phase, after we've set up our project, we've applied our loading conditions, set our objectives and our manufacturing types and materials. The next phase would be to explore the results we've actually created. So here we can start making those trade-offs we've been talking about, and then we'll send out that solid CAD file to work with. So through this project, there's a wide range of options. Again, we had a range of materials, a range of manufacturing types. So each one of those materials and manufacturing types yields its own unique solution. So carbon fiber reinforced plastic is going to react very unique to how HP nylon 12 and additive manufacturing might. So here we can take all of those results. We can view them in the thumbnails and the properties that you see. We can also view them graphically as well. So this is really interesting where we can say, show me all of these parts on a specific mass range. We can start filtering them down to specific strengths and stress references that we would like to then find the part that we'd like to move forward with. So the part that we found is the one that you can see on the screen there. So this was, again, that HP nylon 12. This was meant to be an additive solution, so it kept that minimum thickness that we required for this project. And it also met the mass target of the 0.14 pounds that we wanted to find for the adapter. So moving forward, and we won't show too much on this project with it, but after we've sent out that solid CAD file to then move forward with, we have the ability to post-process that. So this could be adjusting the actual surface geometry itself. It could be adding a part number to it, or whatever we need to do to get it fully ready for the production process. Again, the real value here is that the generated part that we've created is usable CAD that we can send back. And then finally, the last phase, which is fabricate. So after we've generated a component, we've sent it back, we've post-processed, we're ready to connect this with the additive manufacturing process, and we'll show that with NetFab, which is Autodesk's additive manufacturing platform. Oh, I guess we do actually have the handle as well. So we showed the adapter, but it's going to be a very similar process for the rest of that component, where we're setting up our geometry space, creating geometry to call out as obstacles where we know we can't generate any, applying our loading conditions, setting our manufacturing and material types, and then solving as well. So this same way that we did that process here for the handle component as well. So I'll fast forward a little bit in this video. You can see we have the generative user interface again. The green is the preserved geometry for the outside of the handle. And again, we're applying our loads and constraints to this part. So with the adapter, we had about 7 or 8 load cases, and we would do the same for the handle. So after we apply all the load cases, again, we talked about the ability to set a specific mass target for the adapter, which would be lower than the operator's hand, to even that out to the top. So in this case, we can put a mass target that's going to allow us to say that on top of the hand is going to weigh the same as on the bottom of the hand as well. Same thing with the manufacturing types, like we did with the adapter. We can put in our additive manufacturing requirements, and we can also explore those subtractive options as well. And then exactly the same, we always want to explore as many material options as possible. So we could select up to 10 the same way that we did with the adapter. And then finally, after we've set up that project, we can then solve it and then start to explore all those options. You can see I've ran this one a couple different times. So there's a wide range of results that we received from that, over 140 outcomes. And it's important to note as well that within each one of the outcomes, there's also a range of iterations that we can choose from. So if you see that slider at the bottom of that one outcome, and I'll pause it right here. You can see that this one ran 13 iterations. All of the iterations leading up to this final converged solution are also viable, usable options that we could move forward with as well. So after we've found the iteration and the outcome that we'd like to move forward with, again, we can send that out as usable CAD geometry that we could then continue to adjust or run through FEA, or we can continue to produce. So after we've set up the adapter, generated our outcome, and we've generated our handle outcome as well, the next phase would be to fabricate. And this is through Autodesk Additive Manufacturing Platform. So what we need to factor in here is we're looking at the HP multi-jet fusion process, which one of the great things about that process is that it allows for 3D packing. So if you're not familiar with that, you can fill almost the entire volume of an HP printer with components. So allowing you to drastically improve the efficiency of your process. We can look, and then just verifying that minimum wall thickness was met. So again, the first thing that we would do is we would bring those components inside the HP multi-jet fusion workspace. Within that workspace, we can take a look at each one of the components. And one of the first things you typically always do is you might repair a part. So in this case, there weren't any issues with the part. It came in as a watertight solid, as you would expect from sending it out through the process that we just showed. We can also run a minimum wall thickness test to say, make sure that all of the features within this component would fit the minimum wall thickness that the HP process allows for. And you can see that this is above the threshold in saying that this passed. Again, we set that minimum wall thickness when we were setting up our project as well. So the next phase, and again, this goes back to the idea that we can fill an entire printer's platform. We really want to try to get the most out of this process. So there's a couple different ways to do it. We can 3D pack an entire platform with these components. So again, we can print as many as possible within one print job. So here we can do what's called a Monte Carlo 3D packing, which takes all of those components that we brought in, and those could each be their own unique order, and then it packs the platform of that printer to fit as many of those parts as possible within one setup. So now that we've set up the adapter, we set up the handle, we generated outcomes and then produced those, I will hand it back to the team from Penumbra to talk a little bit about the outcomes.
Yeah, so yeah, we're going to kind of go back through some of the same things we talked about just to kind of recap, and then we'll kind of go into some of the economics a little bit too of this part. So really the additive advantage for this product was that we can make it better than traditional means, 78% improved strength compared with the conventional design. And a big one too is isotropic part properties. So a unique thing about MJF versus like an SLS technology is that it is nearly isotropic, so that we can actually do simulation accurately and be able to basically take the loadings in X, Y, and Z and have good results from that, unlike an FDM type technology where we're dealing with the layering and the strength between the layers, so that is inherently anisotropic and very hard to do simulation on. And even processes like SLS vary a little bit in other directions. And then the customization possibilities was probably one of the big pluses for our customer, just to be able to take that bottom adapter and make it flat, curved, or unique shape, because the function of the product depends upon the coupling of that transducer up against the surface of what it's reading. So that was a big plus. And one of the benefits too for making this a business case was that with no tooling, 17 full assemblies could be produced within 24 hours with a 4200 series machine. So depending on how you buy this part, so through like a service bureau, we're looking at $338 per unit. And then in-house production, so say if you had a 4200 system in-house, depending on what your markup is, it could potentially be roughly a third of that, $113 per unit.
And it's important to note too is that the unit would apply to the entire assembly, right?
Yeah.
So it'd be about 6 or 7.
Yes. So that's all the plastic components. So it's even these two plus like a front cover and then a bottom cover on the adapter. So that's the entire unit.
This is Dean. You know, I really love that other slide where they talk about just the benefits from like a pure engineering perspective. And one thing that we've been trying to do is actively making use cases and business cases for all of this stuff. I myself, as an engineer, I desperately love things that you can analyze. The nylon 12 that we've used has made all of our predictions very accurate for the load cases that we've been able to push through on this particular unit. What I really like about it is that you can actually optimize everything from like two perspectives. Like you can actually use engineering in general as a methodology to be able to provide an upfront user cost, you know, and create something as efficient as possible. And then on the back end, you can also save costs using the additive stacking method or nesting method. And I'll go ahead and hand it off to Steve.
Yeah. So as we're planning this out, and creating basically this optimized part, not only on the engineering side but the business side, we can show these numbers, and additive manufacturing, we create this predictive kind of flat line model, because we don't have to deal with tooling. You see the starting costs there for injection molding is based off of $150,000 worth of 5 molds for the 5 individual components that make up a unit. So yeah, if we want to get the unit price to basically an optimized position, we're looking at, with an additive in-house service, you could really go up to almost about 1,000 parts, and really what I have 1,100 units in-house production, and you're better on the cost side versus injection molding. And even with a service bureau, you're looking at roughly about 500 parts, being able to make the cost per unit basically match that of injection molding.
And for what these types of applications are really used for, they typically, in the use cases we've had so far, they're all specialized things. So you're really not going to be going much further in excess of either 500 or 1,100 units. So if you fall within that realm, you're always guaranteeing tremendous cost savings using this form of additive manufacturing in conjunction with generative design to maintain that level of efficiency.
Yeah, and one thing too that I want to mention, this graph doesn't show what happens, say, if we need to modify a mold, if we need to buy a new mold. So this just allows us the flexibility to not have to deal with that. We don't have to deal with the amortization of a mold over time and making our money back that way. We can go to a service bureau, we can figure out the price, cost per unit, and then we can change the design as needed, make improvements, and really all those benefits together make additive just an optimal option for this use case. So yeah, next steps. So Matt kind of talked about, on the Autodesk side, where to get plugged in with Fusion 360 and Generative. Penumbra Engineering, we are a product development services company, and one of the things that we like to push is that empowerment of additive manufacturing. So we'd like to announce during this webinar that we're going to be offering a new online course coming in the next few months called 3D Printing Mentality. It's going to be a virtual-based class, so you can access it online. And really the idea behind it is bringing your innovative product ideas to life using 3D printing. And we will be talking a lot about generative design and about the return on investment that you get with additive manufacturing. Because really, at the end of the day, the engineering is very important, but the ROI is also important too. So we want to kind of dive into this in this online course. We're going to be offering probably a mini course at first, that's a free version, and then going into more of a longer paid version. And I'll give you some information if you want to kind of stay in touch with us about that. But just kind of touching on the product life cycle kind of model over there. One of the important things that we focus here on Penumbra is really not additive in one spot in the product life cycle, but how does it benefit throughout the entire life cycle? Where are its benefits really taken advantage of the most? And then also one of the things that the use case that we mentioned too is a lot of people can start to implement it, but how do you go through a proven process and step by step through different phases throughout the project lifecycle to arrive at a result that meets customer expectations, is a better part, is an innovative part. And so we're going to be diving into that into this 3D printing mentality course.
Yeah, this course in general is gonna be module driven, and it's like I'd mentioned, it's going to be a collaborative in nature and how we actually teach the course, but it is going to be overviewing this product life cycle. One of the important things that we've been trying to smash has been that using additive manufacturing when it comes to the product development I think from a traditional perspective has always been used in the prototyping phase, but we have been using it for end product, and we like the idea of being able to use it throughout the entire life cycle, like Stephen had mentioned. And with this course, even with the accelerated one that we'll be putting out here at the very beginning, it's going to touch on some of the things that we do, a lot of the things that we have learned over the years that we've been trying to develop this method, and some of the things that you should do, things that you shouldn't do. And hopefully it turns into, like I said before, a very collaborative type environment to be able to learn and improve both your product or your service bureau if you're like us and you're an engineering company. But for the most part, I think as we start rolling through here, we'll be sending out a little bit more information about some of the modules. The first ones that we're going to discuss throughout this are basically going to be, can this product that you're trying to make be 3D printed? Should it be? And helping work your way through a nice and conceptualized process to be able to determine the appropriate application for what it is that you're trying to do. The second one will be related to product conceptualization. And that's something that many of us, have probably been through, and especially if you're an engineer. My personal favorite is going to work through the research and development phase of all of these things. Then we'll roll into another favorite of mine, which is prototyping and testing your beta product. And when we start getting through that beta product, we're going to talk a lot about how you actually ramp this stuff up for low volume production, like we talked about a little bit before here today.
Yes, when that comes up. Yeah, so if you want to keep in touch with us, there's our website. So if you go to our website and go to the Contact Us tab up in the right corner, and there's a drop down and it basically says sign up for our newsletter. So we'll kind of be sending out notifications for this over time, and you're also welcome to email me with any questions about any of that. And but yeah, we're just really excited. We're excited to dive into generative design inside that 3D printing mentality course too, to complement what we've talked about here with just the Autodesk generative design offering, and really showing you what the technology can do and where it's kind of progressing into the future.
Great, thank you for that. And just one more quick close from the Autodesk side as well. Again, if you don't have a commercial license for Fusion 360 to try generative with, you can get a 30-day commercial trial, which will have cloud credits you can use for probably 1 or 2 projects. So you can see that link there on the screen, and I'll share it at the end. And then also, I'd highly recommend taking a look at the Fusion 360 adoption portal. Again, it has great content for generative. So if you want to learn more about the process, you can learn more about it here. And once again, probably more importantly than anything, please feel free to reach out to me with any questions. If you're wondering how you can get started using generative, wondering if your products are the right fit, just please feel free to reach out to me and I'd be happy to help. So we do have a few more minutes, and it looks like we've had a lot of good questions coming in through the chat window and Q&A. Please feel free to also raise your hand and we can call on you live. But until then, we'll just continue answering some of the questions that we see. So there's a question from Thomas in the Q&A, and the question is, do you have any plans to incorporate optimization for thermal flows? So I think improving the generative solve to include multiphysics is something that the team is certainly working on. And Thomas, if you reach out to me separately, we can probably talk more about that. Another question in the Q&A, this one from Alex, is injection molding a manufacturing method generative can optimize for. So injection molding is not specifically a process that we can generate for yet. I think same as multiphysics, it's one of those things that it's certainly on the future horizon for the product. But right now, as far as manufacturing, we can only do additive and subtractive for 3 and 5 axis. And then I should also note, so while we don't technically have injection molding, we don't technically have casting, the fact that we do get usable CAD geometry sent out through this allows many of our users right now to take out an outcome and then alter it for that specific process. So this is a question from Ronald, and maybe this is probably more for the Penumbra team. I'm really interested in pursuing generative and additive for products with 1,000 to 2,000 annual production. What possibilities are there for alternative materials with multi-jet fusion or selective laser sintering? And then he states that he operates in an aquatic environment where nylon might not really be the ideal material. Do you guys know any other material options?
Yeah, so just the regular MJF nylon 12, because it's inherently isentropic, and when it's fused together, it creates pretty much a watertight seal. You can actually use it for certain applications for water, and you can actually use it for reservoirs and pressure vessels. Excuse me. And so, and really that's just based on how you are using generative design in your setup. But MJF, the multi-jet fusion platform, has basically a roadmap into the future of different materials that are going to be coming out. So right now, I think the other highly available option is like the glass bead version that they just started incorporating into the service bureaus. And then you're looking at elastomeric materials, and you're getting more and more into the future. You're going to have flame retardant